And to our honorable speaker, please welcome Dr. Kadi Teknomo.
Thank you, Tamara, and thank you, Joyce. Good morning, good afternoon, or even good evening for our distinguished guests. Today, actually, we have an international attendees. I see people from Indonesia, from various cities and islands, or even like from the US, Philippines, Malaysia, and Pakistan. So as you could see that we are very fortunate to have Mr. Kadi because Pak Kadi already have, Dr. Kadi already have like international experiences throughout the world. So for today's event, we will have two different parts. The first part would be the presentation by Dr. Teknomo for more or less 45 minutes. And then it will continue with the Q&A session for more around 15 minutes. Okay, so before we start for our first part, please let me introduce a bit about our speaker today. So Dr. Teknomo is one of the main proponents of ideal flow network, Teknomo-Fernandez algorithm, and the main contributor of queuing rule of thumb. So if any one of you would like to Google now, Teknomo-Fernandez algorithm, it's really cool. Okay. He was an international consultant for several industries in several countries, including International Finance Corporation of the World Bank Group, Toyota Info Technology Center in Japan, the Savannah Solution in Switzerland, the Probe Software in US, and the RMS in Brazil. Before joining Petra, he was an associate professor in Ateneo de Manila University in Philippines, a visiting professor in Ateneo de Davao, Philippines. But also, Dr. Teknomo is a visiting research fellow in the University of Wisconsin and Blackthorn Incorporated, both in the US and in Austria. Dr. Teknomo also a research fellow in the Austrian Institute of Technology in Austria, and he was also a lecturer in Saga University, Japan, and recently he rejoined Petra Christian University in IPE program. So Dr. Teknomo has a long list of awards and scholarship, but I would like to share one of the newest, which is in 2017. He listed as one of the 150 top researchers or scientists of the Philippines across all fields. And in the same year, he also got award of Outstanding Scholarly Work Award of Science and Engineering from Ateneo de Manila University, and 2015 Ateneo Research and Creative Work Faculty Award. What amazing achievement. Also, Pak Kadi already work with a lot of research grant. The newest would be from 5 years work from Commission of Higher Education of Philippines, working on Philippine Higher Education Research Network. And from also 2013 to 15, the Philippine Council for Industry, Energy, and Emerging Technology Research and Development Department, working on a project called Advanced Traffic and Pollution Monitoring and Analysis System based on GPS trajectory. So without further ado, let us welcome Dr. Kadi Teknomo. Please, Dr. Teknomo, the stage is yours.
Thank you, Nova, for the introduction. Right. Okay, so yeah, thank you for this opportunity to discuss about my research. First, probably is the disclaimer. I'm a theorist, okay? So my work is mainly in the development of a theory. So people often can say, I probably only know theory with no practical application. So that's me. So many practices must have a foundation in some theories. The theories developed by many people, mostly scientists, as our predecessor, have allowed us to enjoy the modern world that we live today. Thus, I'm trying to contribute whatever tiny contribution I can give through my research work. So I'll discuss our talk today into 5 parts. First, I'll discuss about the tools for solving traffic congestion. Then proceed with the development of ideal full network and IFN transport application. Then I will introduce the concept and model of congestion redistribution. And finally, beyond the technicalities, we'll discuss how can we actually solving traffic congestion together as a society. Okay? So let us enter the first part of the tool for solving traffic congestion. So let me introduce about traffic congestion problem. I hate to queue. Okay? I don't like traffic congestion. Traffic congestion is inefficiency problem. When I joined transportation major in civil engineering in Petra about 3 decades ago, I was motivated to solve traffic congestion problem. Unfortunately, until today, we haven't solved it yet. Many people who live in metropolitan areas, Bangkok, Karachi, Jakarta, Manila, will experience heavy traffic congestion on daily basis. Right? So I used to travel 1.5 hours to go to work and another 2 hours to go home. Say, illustrate this, during a bus trip from AIT campus into Bangkok, just 42 kilometers, I sat beside my girlfriend, which is now my wife. I checked the clock every time the bus would move. It was exactly 7 minutes for the bus to move, just about 100 meters. Thus, I decided to go down to look for a toilet, did my call of nature, and then run back to the same bus, sat in the same seat beside my girlfriend again. That was the illustration on how a heavy traffic congestion. So if you live in a city, most probably you have experienced traffic congestion. Almost everyone hates traffic congestion. What can we do about it? Almost everybody has some kind of ideas how to solve traffic congestion that we face every day. A student, a teacher, a taxi driver, or Grab driver, when you are on the road and you face traffic congestion, you will probably comment, why don't we do this or that? The problem is, most of them don't have tools to evaluate their ideas. To simplify our understanding, we can view 3 approaches to solve the problem. First is to do trial and error directly on the field, to use the traditional model. And the third, of course, to use our proposed ideal full network model. Okay. The first approach is the worst way to solve traffic congestion. If you have the power of the government, then you could do experiment directly on the field, whether you're adjusting the traffic signal timing or do the widening of the road or making the bridge. If you do it without proper optimization tool, what you are actually doing in this first approach is actually a trial error directly in the field, which is not only costly, but also irresponsible experiment. Why? Because it will affect the life of many people. So the second approach, which is of course better, is to use the traditional, what is called a traffic assignment model. How to quantify our ideas to solve traffic congestion so that we can evaluate which idea would really work. Traffic engineers, transportation planners have tools to evaluate their ideas, okay, to solve traffic congestion. These tools are mathematical models that will be represented as computer program or simulation. For simplicity, let us call this tool a traffic assignment model. The cost of the software is very expensive, about $10,000 per license plus the maintenance fee every year. instead of solving the problem, actually the traffic congestion problem have created opportunities for their business. So do you think they will genuinely solve traffic congestion that will ruin their bread and butter? The commercial demos are very nice with lucrative animation. You need to be a transport expert just to input the data and to run the program. The algorithm inside this commercial software are often heuristic, and you treat them as black box without knowing how does it work? What are the assumptions behind destination or flow based on the weighted. It's again another assumption. Okay. Sampling traffic flow survey data will also become another source of data to calibrate the model, which is to adjust the model parameter. To predict, the engineers and the planners will forecast the population and the economic of the zone. Based on this socio-economic forecast, then the future traffic flow will be estimated. We are what we model in our mind. This current traffic assignment model have many common unstated, sometimes hidden assumptions, which causes the problem, which I would like to debunk. First assumption is home-based traffic. They model only one way, okay, from home to other places, such as workplace or school. And they assume that we go home. When we go home, we will simply use the other direction. Because of this assumption, okay, we have traffic congestion in one direction and almost empty in the other direction, isn't it? It's often happens. So the network, the road network is not efficiently utilized. Why this efficiency problem happen is due to the second hidden assumption, which is called weakly connected. Okay. What does it mean? It means the current tools of the transportation planning will have the source node at the origin and the sink node or the centroid at the destination of the tool. Because of this assumption, they require extensive input of the tool. Unfortunately, the OD data is tremendously expensive to gather. And without this data, we are not able to model properly. If you input with any data, then garbage in, garbage out. Okay. So the transportation network, okay, is actually should be what is called strongly connected network. So if one can only go somewhere but cannot go home, then it is not a transportation network. Okay. So one of the hidden assumptions of the traditional traffic assignment model is weakly connected network. Because of this assumption, okay, we can see the result in the inefficiency in utilizing the network. In reality, transportation network must be a strongly connected network. What do I mean by strongly connected network? It means that if you go from your home somewhere else, you must be able to go home, right? In a weakly connected network, which is the network with the source or sink node, from your home, you can go somewhere, then there is possibility that you cannot go home. Thus, our third approach to solve traffic congestion, we will introduce what is called ideal flow network or IFN. Okay. So I ask questions what will happen if we remove this assumption in the traditional traffic assignment model? Can we build a better tool that eventually will solve the traffic congestion? The answer is quite surprisingly yes. And I'm going to tell you how and why is it better. Okay, so one of the tools that I have developed is IFN or Ideal Tool Network with at least 3 variations of different programming language. Okay, one is in Python. These are the link for the GitHub, which is free, including the source code. And we have also in Excel, you can also download. And we have also the JavaScript version is currently still under development. Okay, so in contrast to the traditional method, okay, I have developed IFN Transport, which is of course free, okay, available in GitHub, including the source code. So IFN Transport is a transportation planning tool, okay, to give the estimate of the traffic flow, the traffic congestion, speed, the density, travel time, the delay, okay, based on the concept of IFN that I will explain in a few moments. Okay, so using this tool, you can download OpenStreetMap data. Okay, so if you use the OpenStreetMap directly, the website directly, you will get maximum only 50,000 nodes and this kind of XML file. Okay, but using IFN Transport, we have lived up this limit. And furthermore, the software will assist you in downloading the OpenStreetMap and then converting into network graph, and then automatically clean the data into the largest strongly connected network. Okay, and it can also be used to calibrate the model with the real world data. Okay. Talk with this about the IFN development. Okay. I asked, what will happen if we remove those assumptions in the traditional traffic assignment model? And a better tool where, and then must be able to go back to the original node. Okay. I created hundreds of agents that move randomly from one node to the next node based on the allowable direction. And then the movement of this agent will create trajectories, which is the sequence of nodes passed by the agent. And then we'll record the link flow, okay, which is the count of aggregation of how many times the link has been passed by the agent. So I was expecting a good result will come out of this random walk experiment. But unfortunately, I did not see any good result. The flow, which is the aggregation of the trajectory, keep increasing without bound, okay, to infinity, as I increase the number of random walk agents or the simulation time. I also tried to find various relationships with the network properties, but I could not find any nice pattern because the flow keep increasing. But if you look at this, okay, my curiosity keep growing. About a week later, I staring at the flow result, something like this in very detail. You can see this is 8,000, this is like 17,000, like double, right? 17,000 and 34,000 is like double again, right? So there is some pattern here that only our intuition can capture, but the so at one point of this exploration, I got what is called Eureka moment. Okay? I divided each of the link flow with some network statistics, as the total flow, the average flow, or the maximum flow, or the minimum flow in the network. And they give similar colorful unique pattern in its network. Okay, whenever the computer simulation reaches infinity, if it is very large number in the simulation time, okay, this is the asymptotic value of the link relative flow. They are integers, okay, close to integer, and the simulation is converged. Right? They produce a stable values of unique pattern, and since the flow pattern only happen at the point of infinity, in short, ideal flow is a limiting a relative link flow distribution of random walk, okay, at this point in a strongly connected network, given the probability distribution of outflow in each node. Okay. To show you the process, let us take this simple network, example of 5 nodes. Okay. The A here is the adjacency matrix of this network. So I do it in Excel here. So you see here the flow is keep increasing on the top, okay, but the relative flow will eventually convert to a certain value. Right? And if you look at the sum on the right side and the bottom, okay, they eventually become almost the same, right? So, and the total of the sum of columns and the sum of rows become exactly equal. Okay. And we can, of course, instead of every links, we can also see the convergence also in every node, right? So this is very interesting in phenomenon. Okay. Regardless the number of agents, okay, or the total is call this ideal flow network or ideal flow matrix in this case. Yeah? So, and this interesting finding because the asymptotic flow ratio is actually a good indicator of how the link is utilized in the network. Okay, and now we can see, we can play with the network topology rather and based on will be exactly the same also. Okay. So when we put the flow pattern in the property, pre-magic matrix is a matrix where the vector sum of its row will be exactly the same as the transpose vector sum of its column. Okay. So what does it mean? Pre-magic matrix indicate the flow conservation, right? So only when the network is strongly connected, then the random walk on the network will produce flow conservation. A strongly connected network is not necessarily pre-magic, okay? But pre-magic properties only happen when the network is actually strongly connected. Okay, now if you have only small network, we can actually do the IFN manually, okay, using only pen and paper. Here's an example of small, strongly connected with only a few nodes and links. For simplicity without losing generality, let us take an example of equal flow. Okay, we can later change probability distribution in value 100 to one of the link. Then we trace the flow in each node based on the flow preservation. Okay, so in each node we set up the balance equation that the total inflow will be exactly the same as the total outflow. When the flow in all nodes are balanced, then we get the ideal flow. So you see here from 100 in drawing A, because equal flow, so we divide into 2, so 50-50. In drawing C, the 50 will be divided again into 2, it is 25-25. And then in drawing B, divide again into 2, become 12.5 and 0.5. And then you can see this is the 12.5 continue. Okay, so of course we can divide this with the minimum example. So 12.5, we get the last drawing in F, which is also called cardinal network. Okay, so we simply, to make the integer, you can put all the flow numbers into rational format. Then you get the least common multiple, or LCM, of the denominator as our global scaling. Then simply multiply to all flows in the network with the global scaling. Okay, so of course using random network, random walk on network, or manual computation, we can compute, okay, for small network. But for we must use optimization procedure based on maximum entropy or based on the solution of Markov chain, okay, which is generalized inverse formula. Okay, I will show you in a moment. So if you are not familiar with Markov chain, I will introduce in a brief. So in Markov chains, okay, we have any network with an agent, and then its node. In its node, okay, the agent will choose the decision, okay, based on local information, where to go, okay, to the left, to the right, or straight. And then this local information is in terms of stochastic probability, okay, where the sum of probability in its node is of course 1. Okay. When the agent have passed the node, and then the agent will forget the previous decision, and again use the local information on the current node. So if you look at this process, okay, this is exactly the same as our random walk. But the theory of Markov chain has allowed us to use a matrix and linear algebra, okay, to solve the random walk. Okay, so of course, I will skip the detailed mathematical derivation of the Markov chain. Okay? But if you can contact me if you are interested in the detailed derivation of this formula. Instead, I will show you the steps, okay, of computation with a numerical example. Okay. What does it mean by this formula here? Okay, first we subtract the stochastic matrix. The transpose of the stochastic matrix with the identity, and then we concatenate with the row vector of 1, okay, to form matrix K here. And then again we concatenate the zero vector with the total flow kappa to form vector T, and then from here we can find the left generalized inverse. Okay, I call this K plus. The formula is just simple here. And then we compute the node vector P, okay, via matrix multiplication with the generalized inverse. So this is the example. Okay, so suppose I have the stochastic matrix here. So, and the total flow kappa is 1. Let's use this simple example of 4 nodes only. Okay. And first we transpose the stochastic matrix, and then we take the difference with the identity matrix. Okay. And then we form the matrix and the vector K and T, right? And then we find the left generalized inverse, and then we computed the node vector. Okay. From here, we can distribute into the ideal flow. Okay. So we finally will obtain the flow matrix, which is of course prima-check. Okay, the sum of rows is exactly the same as the sum of columns. So for those who are not familiar with the maximum entropy, here I will introduce it in brief. Okay, suppose we have 5 slots. And in each slot we put one number, say 6, 2, 4, 5, and 3. We can calculate the statistic. It's the total on the average of, how much is the total? 20, right? And the average is 4 in this case. So now let us do an inverse problem. Knowing the statistic, say the total of the average, we want to know the data. Suppose I deleted the number in the last slot. Can I get back the average of 4? Yes, right? Because we know the total, right? So we can deduce the missing value is 3. Say, we say the degree of freedom of the statistic is 1. So what if I deleted the last 2 slots? Okay, so what number will fill in to the 2 slots in order to get the average of 4? And something like this. And what happened if I deleted 3 slots? What number should I fill in these 3 slots, okay, in order to get the total average of 4? If you said, okay, I will fill back the original value, that is not true. Okay. So if you fill up the original value, that means you knew something about the probability distribution of it. You already know the data. Okay. Suppose you know nothing about the data. You know nothing about the probability distribution of this missing slot. What you will fill in? Of course, the most common sense is to assume uniform distribution, right? Okay. So if you have 3 in here, so the total must be 12 divided by 3, which is 4. Okay. So maximum entropy is exactly that. So suppose you have this data, you get the total and the average, right? And if I deleted that 3 slots, what will happen? What should I fill in this value? Then we can calculate the probability. Okay. And from this probability, I can also calculate the entropy. Okay. So from the entropy, we can do using solver and maximize this entropy, right? And then subject to constraint, the average should be 4. Then you get exactly that, okay? 4, 4, 4, approximately. I hope you get the idea of maximum entropy. So if we don't know, we shall assume uniform probability distribution. Because when we don't know the probability distribution, okay, the least assumption is to assume uniform probability distribution. So maximum entropy is exactly a method, okay, to compute the common sense that we just discussed. Okay. By computing the entropy, then use the Excel solver to do maximum entropy, we can get that common sense value. Okay. So maximum entropy is also mean that this is maximum depth. Okay. So to use IFN based on maximum entropy, we need to define several things. Okay. First is to define what is called node entropy. So from the stochastic matrix, we can calculate the node entropy. And then we can also get the total of the nodes value, which is kappa. This is in the total flow. And then the network entropy is basically the weighted average of the node entropy, right? So from here, we can formulate the optimization of the IFN. Applying this maximum entropy principle, we can set the optimization to get the IFN as follows. So our goal is to find in each node, okay, then what is the link value, which is the value of the node, the flow. Then we distribute this flow to all links. Okay. So the probability distribution, which is the best represent the current state knowledge, is one of the largest entropy. Okay. So in this context, precisely stated by the prior paper. So maximum entropy principle will guide us to select a consistent model with, in fact, consistent with the that we have. So applying our optimization formula into Excel, again, using the solver, we can solve this. Okay. Now, let us go back to the ideal flow network, or IFN. We can view the solution of traffic congestion. One is the supply, and the other one is the demand. The supply part represents the network connectivity, the link capacity, or the distance, while the demand side will be the flow or the origin destination flow. Okay. Work, and then the route choice program. Okay. In contrast, the IFN will combine these three components into a single stochastic matrix, which represents the microscopic OD matrix. Okay. So in principle, the input of IFN model is the stochastic matrix S, right? And then the parameter of the model is the total flow, kappa. Each positive entries of the stochastic matrix here represent the outflow probability of a link in proportion to the total inflow. So outflow divided by total inflow. If we look at the size of this input data, okay, you will not wonder why IFN can actually fit any data. The number of input parameter is huge. Using ideal flow network, it would require much more data than the traditional traffic assignment model. Say, in traditional traffic assignment model, we would require only macroscopic zonal OD, yeah, origin destination matrix. This number of zones of the city usually less than 200. In contrast, the IFN will require the stochastic matrix, the stochastic probability of all links in the network as the input data. And these probabilities would serve as the microscopic origin destination in each node. The typical network in a city usually have about 500,000 nodes or links, okay, or even more. At first glance, this seems like an unsolvable problem, isn't it? Because the IFN model required much more data than what we need to input compared to the traditional method. Okay. However, if we look at it in the detail, okay, we can see that the stochastic probability is actually outflow probability in proportion to the total inflow. So the probability can be approached in many different ways. Okay. One of the simplest will be to get the outflow proportion of the link capacity can be used to approximate the stochastic probabilities based on the network structure. So given the capacity matrix, we can find the approximation of the stochastic matrix, okay, via the Hadaman efficient. This is the formula. Yeah. Because ideal flow is relative flow, okay, we can also globally scale with the positive scalar. Okay. For instance, integer value without changing the stochastic matrix. So this is called equivalent ideal flow network. This is the basis for the calibration. Okay. For example, if we know based on our observation that this link flow is say 1,500 vehicle per hour, then we can calibrate the IFN. We can find the global scaling factor that make the result of our model close to that observation. Of course, the more data that we have, then we can have a better model, closer to the reality. We can also obtain the R square, and sum square of error of this approach. And interestingly, if we invariant. Now, equipped with those theories, we can start to apply. So the IFN transportation. So everyone can comment to give opinion on how traffic congestion can be solved, right? But usually we don't have the tools to measure. So to prove this, how we will apply the idea of IFN. So you can create this type of scenario that we can apply for IFN based on the change of the structure of the weight, change of the link, change of the node, change of the path, or change of the stochastic matrix itself. So these are the examples that we can use. So for the application scenario using IFN. Two examples. So our first policy scenario is I want to add link. Suppose we have a very simple network, and then the number like this represent the ideal flow. So
masker luar mungkin maunya dibuang aja ke duluan tadi.
This add link from node 2 to node 5, and we get the new ideal flow. And in figure C, again, I add another link from node 1 to node 3, right? And you see here the maximum flow, which is of course if we assume the capacity, then the maximum flow is the same as congestion. The maximum flow here is 4, which is actually much larger. So we will think that if we add more link, is it meaning that we'll get more congestion? Then I add again another link here. In figure D, which is the red link is I added from node 2 to node 4. Again, the maximum congestion increased to 6 here in node 1 to 5. But look at this. In B and C, the congestion, the maximum congestion happened near the link that we added. But here in figure D, the congestion is actually far away from the link that we added. From here we see, can we actually reduce the traffic congestion by adding link? So when we add from figure D, we add another link from node 4 to node 1 here. The maximum congestion diffused from 6 to 3.5. And another scenario is from D to E to F here. I add link from node 3 to node 1. Again, it reduced. So the meaning is we can actually scenario analysis to find the optimal link that we want to add in the network to reduce traffic congestion. So say we have another scenario. How about if we add the lane? So say we have a simple network of 6 nodes, the lane capacity are stated in the network. Okay. So, and we would like to compare if we add just one lane in link DE here. Okay. So the base scenario has 2 lanes, and then in the alternative scenario, we have 3 lanes. The rest of the network remain the same. Okay. So these are the scenario parameters. So we say that the capacity per lane is 1,800 PCU per hour. PCU is a passenger car unit. Okay. And the total demand supposed to be, say, 17,500, and maximum speed is 40. Link length is assumed to be 1. Okay. So then from the capacity of the lane, we can put into the real capacity in terms of a passenger car unit per hour per direction. Okay. And then from this capacity matrix, we can compute the stochastic matrix, okay, based on proportional capacity a while ago. And then we can compute the ideal flow. And then we scale, okay, the ideal flow to get 17,500 total flow. Okay. From here, we can calculate the congestion. Okay. Congestion is simply the ideal flow divided by the capacity. Okay. So we see here the maximum congestion happen in link DE, okay, 0.9. Now, then we can compare. Okay. Based on this, we can calculate the travel time, the delay, and the speed, and so on. Okay. So we can in this case, right? Another application is now, because we have the ideal flow network, okay, then we can actually only say this is an example. Okay, based on the scenario network here, see the total flow is kappa is 27. Okay, the maximum flow in this case is link AB, right? 6. Right? So the question is, which one link I want to add into the network so that the greatest reduction of the maximum flow will happen while keeping the total flow, which is the total demand, to be constant. Then of course we can search. Okay, we can use program computer to search the scenario, and then the best link to be added is, say, link CA, which will improve the reduction of congestion, say, from 22% to 16%, and so on. Now, we can also use better than that. Okay? We can also use IFN to do a long-term prediction, to predict not only the congestion, but we can also predict where and when the traffic congestion will happen, okay, based on certain policy scenario. Say, this is an example, okay? The policy is to add one lane on the most congested link when the maximum congestion rates 0.9. Okay, so we assume there is no change in the network. So we also assume capacity per lane is 1,500 vehicle per hour, and the city population at the year 2000 is, say, 1,200 person, and the car population is 550 cars, and so on. Okay, and we have this model of the population growth. Okay, so 5 years, and then 5% per year. The car population growth is 7% per year, and then the total flow in the network is assumed to be using this socio-economic model. Right. So this is the base year scenario of 2000. So we have the lane capacity, and we convert this into a vehicle per hour. The stochastic matrix, the ideal flow and the congestion. And we found out the total, the maximum congestion is 0.61 in the year 2000 in link DC. Okay, we take note on that, right? And then we want to predict, okay, when will the maximum congestion happen to reach 0.9? Okay, so the maximum congestion will reach 0.9 when the total flow will reach 16,156, which happened in the year 2009. So we can tabulate this, okay, to calculate, and then the year now, the base scenario now become 2009. We compute again the flow matrix and the congestion matrix, okay, which of course 0.9 happened in DC, like a while ago as predicted. And then we check if this happened, okay, then we need to add one lane in the link DC, right, in the year 2009. So because of adding one lane in link DC, the congestion in link DC becomes 0.6. Then the congestion, maximum congestion shifted in another link, which is B, C, and BE, the one in red here, with to be 0.82. Then we ask again, when will the maximum congestion level reach 0.9? Okay, and we compute it will happen when the total flow reaches 17,000 something, okay, in the year 2011. So we can continue the computation in the same manner, and we will know, okay, this is like the summary here. Using IFN, we will be able to predict when, which year, and where, which link the traffic congestion will happen, okay, based on a certain policy. For example, the policy is to add one link, okay, on the most congested link when the maximum congestion reaches that certain threshold. Okay. Now, as the the government usually work based on myth that adding lane will actually improve congestion in the network. Why is it a myth? Okay. Because when we improve the congestion in a link, it might get worse. It may worsen the congestion in other link in the network, as I just showed a while ago. Okay. Right? The traffic congestion is actually non-linear phenomenon. Okay. So if the flow per capacity, say, larger than 0.8, then the delay and the travel time will become suddenly severe. So now I would like to prove that we can also do reduce the lane, and then we can still improve the congestion. Okay. So this is a very simple example with only a few nodes here, five nodes. Okay, so this is the base scenario capacity. Okay, let's say the total flow is kept constant, the demand does not change. Okay, so 27,500. That's in the short-term period. Okay, the capacity per lane is assumed to be 1,500 vehicle per lane. So this number here, C0, is actually the number of lanes. Okay, now observe the number of lanes in link AC. I put in blue here. This 5. Okay. Now we computed the flow matrix and the congestion matrix. The maximum congestion happened in link CD, which is 0.85. Okay, above 0.8. Then what will happen is we improve, okay, the scenario by not increasing the number of lanes, but reducing the number of lanes from 5 lanes to 2 lanes. Okay, from 5 lanes we reduce to 2 lanes. Okay, and we computed again the congestion matrix you see here, it's actually improved. Okay, the maximum congestion now from 85% now become 80%, right? In link DC. So we reject the hypothesis policy that the reduction of number of lanes would always make congestion more severe, redistribution of the congestion. Okay, so IFN can help us to see the interdependency in the network, right? So another example here is actually given the network, okay, IFN can also be used to find the ideal of the ideal. What is the ideal number of lanes capacity without changing the network structure? So, okay, it turned out that when we use the capacity proportion as our estimation for the stochastic probability matrix, okay, we will get the uniform distribution congestion when the capacity matrix is actually premagic. So I call this premagic equilibrium. Okay. At this condition, okay, we also have what is called Nash Equilibrium. Okay. So in game theory, we learn about Nash Equilibrium. Okay. In transportation engineering, Nash Equilibrium is also called user equilibrium or the first wardrobe principle. So we learned that premagic equilibrium is actually Nash equilibrium in the sense that equal travel time per distance. Because the driver cannot move to another route without facing similar congestion level. Okay. And better or worse in terms of the congestion level. Okay, so this is the example. Okay, so we have a simple network here. The capacity is in the yellow. Okay, and then we computed the flow and the flow per capacity, which is the congestion. Okay, and you see this the congestion, maximum congestion is 0.8755, which is above 0.8, which is bad, right? And then again, look at the DC here is 7 lane, and we reduce it to 4 lane. Yeah? And if you look at the sum of rows and the sum of columns in the capacity matrix, exactly the same. So they are premagic. And the flow per capacity, which is the congestion level, now become all equal. Okay, uniform distribution, which is below 0.8, yeah? Just 0.77. So this is the example, okay, that we can redistribute the congestion level. Okay. And this is the system Nash equilibrium. Yeah? So we reduce the number of lanes from 7 lanes to 4 lanes, and the result is actually we redistribute the congestion to the entire network to be lower than 0.8. Okay, so then we go to the main topic of today, which is congestion redistribution or rebalancing the congestion. So the previous discussion is just an introduction. Okay. So having those knowledge of ideal flow network, okay, now I would like to introduce the concept of congestion redistribution. The question is always which one first between the chicken and the egg, right? So until recently, the traditional transportation planner will say the demand will control the amount of the supply. Okay? It seems like the most optimum approach. We let the certain road link to be congested, and we started to add more supplies. Say, for example, the road width, okay, to cope with the increasing demand. At certain point, the road cannot be widened anymore. Okay? Say, due to the demand of the space for living and activities, and or the land prices increase, make the road expansion is actually economically infeasible unless it's done by force of the law. Then to cope with the demand of transportation, we build public transportation, right? we prohibit the single car user. We realign the land use and so on. So we call this transportation demand management. When we only think that the demand control the supply, we can only add the supply or control the demand. That's the only option. Okay? Since our economy and population are increasing over time, then adding the supply and controlling the demand are extremely difficult tasks. So a new approach is actually necessary. So IFN approach is more holistic. Based on IFN, we acknowledge that demand may control the supply as the past human past wisdom. We have built the road at certain width, right? Because of the past demand. And we don't stop there. In addition to the past wisdom, IFN concept open up new possibilities based on the acknowledgement that the supply might also control the demand. The basic idea is having the possibilities to correct the supply to make the demand change to cope with the supply. The correction of the supply will create a new equilibrium to balance the congestion in the entire network. So the demand can be rebalanced via supply chains. That's the idea. Okay.
Excuse me, Dr. Teknomo, another 5 minutes, please. Thank you.
Thank you. So we can redistribute the congestion by reducing the number of lanes in a specific link in the network, or deleting the link as the way to lower the maximum congestion on the network. Okay. After applying the policy, for example, road narrowing or making the pedestrian-only zone of the congestion redistribution, the maximum congestion of the network will be lower. But of course, the average travel time, the network will be slightly worse. Okay. Similarly, the average speed and in the network will be slightly worse before the policy. The argument of congestion redistribution would not be accepted if we keep using the average travel time or average network speed as our performance indices. Instead, what I suggest is to use the maximum congestion as the performance criterion. Why? Because maximum congestion happens in one of the few links. One often mistakenly think that this is actually a measure of a link. In fact, maximum congestion is actually measured in the network, not in the link. Okay. So using maximum congestion in the network is a better performance index than the average travel time or speed, because our goal is actually to reduce the congestion level in the worst link in the network. When we focus on the network performance, okay, the only way to solve the traffic congestion is to widen the road, to add new links. Okay. Once we free ourselves to the new paradigm using maximum congestion in the network as our index, okay, which would happen in a specific link, okay, then we have better options. Now we have, we can both simulate the scenario of road widening or not road narrowing. We can also simulate the adding link or link removal, okay, to evaluate, for example, the feasibility of making pedestrian-only zones. So the reduction of maximum congestion is also similar to make the congestion distribution closer to uniform distribution. So earlier I mentioned that when the capacity matrix is pre-matrix, the congestion is uniform distribution. So then the pre-matrix equilibrium will become the ideal of the ideal flow network. So there are many measures we can use. Okay, so these are the few measures that we can use. One is, of course, to use entropy ratio or relative entropy. We'll just brief it. So this is the FARP index, which is the difference between the maximum of the congestion and the average of congestion. Okay. And we can also use relative entropy In machine learning, we often call this Kullback-Leibler divergence or KL distance. Okay. And this is the example of the relationship between these few indices that we just mentioned a while ago. Right. So as comparison, okay, when we do a redistribution of congestion, we can reduce the maximum congestion, and we make use of the more efficient road network. We can actually also reduce the concentration of the air pollution. And we have more feasibilities of the alternative policies as narrowing the road or pedestrian only zone. Okay. It's not happening in the traditional method. Okay. So yeah, this is the pros and cons that we just mentioned a while ago. So here is the role of traffic information, such as Waze or Google Maps. Okay. The public trust on the traffic information can be utilized to guide the driver, not only to avoid congestion, but also to travel on the less congested road, right? So in this case, the air pollution will be spread and will give us give better chance for the nature to clear itself. So at the last part, I would like to discuss a general term, okay? Beyond the technicalities, how can we actually solve traffic congestion together as a society? Traffic congestion has been considered as a wicked problem that cannot be solved, they say. The crucial question is whether traffic congestion can be solved. Yes, we can actually solve traffic congestion. How? Right? So if we focus the solution within the transportation itself, probably is difficult because the increase of the demand, the economy, okay, will always create a positive feedback loop to increase the number of roads, to widen the number of lanes. So the solution of traffic congestion is not within the transportation itself. Okay? The solution is on the activities. Borrowing the word from the late Professor Mannheim from MIT, that transportation is a derived demand from activities. Then we can actually solve traffic congestion problem all over the world. The key principles is to distinguish the activities that pass information and the activities that pass material, and the understanding of the non-linearity nature of the traffic flow. As we can see in the chart here, between the congestion and the travel time, the curve is non-linear. Okay? Above certain value of the congestion, like 0.8, for example, the non-linearity become very obvious. Okay? Adding more traffic flow in the same capacity would significantly cause the delay. Thus, the reverse is also true. If we can reduce just 20% of the traffic flow, then the build up the congestion will suddenly disappear. Okay. The question is how to reduce that 20% of the traffic flow during the peak hour, right? So one of the old version is to use staggered work hour or staggered school hour. However, during the pandemic, we could learn that the activities as government, business, school, and many its nature is only to pass the information when their work will not be disturbed, okay? Because those activities can be done via online, via the internet. So traffic congestion is actually reduced significantly during the pandemic. So while the internet is already with us about almost 30 years now, humans did not learn to adapt to use the internet significantly yet. We still rely on face-to-face offline meetings. It is actually not necessary when we just pass information. So we need to build paperless society. We should no longer use paper as the necessary document to be transferred. Okay. The government budget for transportation is also separated from the information technology until now. It happened because we did not realize yet that traffic congestion and many transportation can be shifted over the internet. Thus, the policy on IT can no longer be separated from the transportation sector. Okay? Fast and cheap, if possible, free internet connection will be tremendous help in reducing traffic congestion. One day, many of the wide roads that we currently built will be abandoned as we shifted our society toward more information-based society. Until now, for instance, many people still think that document, money, keys are material, which must be transferred via transportation. Okay? But we need to change our old paradigm and think that all things that is information in nature must be transferred via information highway, not the road highway. So only then we can solve traffic congestion problem. As conclusion, we can summarize as follows. Okay? So the IFN is a steady state solution in a relative flow in a strongly connected network to preserve the flow. Right? Now, using IFN as valuable tool for the network, we can actually start experimenting on the topological structure of the network to solve traffic congestion. What is your idea? We can use this tool. And we have debunked the myth that road widening and adding new road is the only viable solution. Look, we build cities for the people to live, not to move vehicles. Okay. As recommendation, so to solve traffic congestion problem, I recommend we continue to use online activities as our post-pandemic if our activities are just passing information rather than passing material. I also recommend you try to rebalance the road network toward premature capacity. So while I discuss here mainly about traffic congestion, the theory of IFN itself can be applied in many other areas of application. It has been applied in health intelligence. It can be used for supervised learning as well as clustering in unsupervised learning. For instance, we can let IFN learn about music and then generate music automatically. It has been applied to learn and predict tabular data. Recently, also, we explored the possibility of applying IFN for a facility layout plan and agricultural ecology. Okay, so if you're the domain expert, I would like to that you'd like to use IFN in your area of expertise. I would welcome any research cooperation with you. And if you are using IFN for your application, you can inform me. Now I would like to welcome your feedback, your critiques, comments, and questions. Thank you for listening.
Thank you, Pak Hardy, for the thorough explanation. Now, there's already several questions, Pak. The first one would be from Feriona. The question would be, is it true that balancing demand with supply can solve congestion? Is this definitely accurate? Then how to apply it, especially for new companies and on a scale level?
Yeah, thank you for the question. So yes, we can rebalancing the congestion by checking, okay, which actually link that we should actually reduce. Not all links we can reduce. Okay, the point is if we can get the premature capacity, what does it mean? Okay, meaning like this. Traffic congestion happens because of choke point, the bottleneck, right? When I say premature capacity mean what? So the total lane that going into the intersection is the same as the total lane that out. That's the meaning. Okay. So by removing the choke point, by removing the bottleneck, of course, you will remove the traffic congestion.
Okay, Pak. So then, thank you, Pak. The next question would be from Caroline. whether the concept and model for traffic congestion distribution applied in the world today are suitable or not, and why?
This is a new concept, so we haven't applied yet, right? So I hope by giving this seminar, you will spread the word to others, and then let others start to apply this.
Okay. But I have a question from me. I'm curious, like you mentioned, like until infinite, right? So in like the road congestion, like just depends on the situation, of course. Like in terms of time, when would it will reach like?
You're probably concerned with the infinite time, but in industrial engineering, about queuing theory, right? And if you learn queuing theory, what is if you look at the derivation behind the queuing theory, is actually also infinite. Okay? And you accepted that, right? Right?
Yeah.
So we use the same approach here, okay, as the queuing theory. Okay, so we use the steady state solution instead of it's a tool to check what is the ideal condition, the same as the theory, queuing theory. So my question, if you can accept queuing theory, why you cannot accept IFN?
Okay. Okay, there's another question from okay, no, there's someone who asked for the recording of the lecture, Pak. Would it be okay to share?
Cool.
Yeah.
Please share this recording to YouTube or any social media. Okay. That would be nice.
Because of in terms of the time, anyone who would like to maybe ask directly to Dr. Teknomo, please unmute and then we could talk, yeah, Pak. I think it's better. Like anyone would like to.
I think there is a question in the chat box from Caroline.
Yes, from Caroline is already asked.
And
yes.
Yes.
And from
another
Fiona,
can
right?
ask directly.
Yes.
Okay.
So anyone who would like to ask, maybe?
Yeah, you can ask direct question if you have any question. Okay, and you can contact me anytime anyway. So, and this recording will be in YouTube, I hope. Right.
Okay, Pak. So sorry, like because we already passed the time and no one may be quite shy, but they might contact you personally through email or visiting your website. Thank you very much, Dr. Teknomo, for sharing with us. So going back to the MC, thank you.
Thank you so much, Dr. Teknomo, for the awe-inspiring session. Personally, Joy, this colloquium has given me new insights regarding the importance of redistributing congestion, and it is truly astonishing that we can solve this with just one concept model. Not only does this valuable network tool give a variety of measures and accurate estimation about the future of street networking, this concept also shows the interdependence in network and facilitates road policymaking in which governments can utilize in an attempt to rectify congestion. But I no doubt that this model is indeed very perspective for the future ahead. Yes, I absolutely agree. I personally learned a lot from Dr. Teknomo, especially considering nowadays problems. Lots of people use their own vehicle rather than the public transportations, which causes more congestion. I believe that this model will be beneficial for all of us in the future. Today's event has provided such great enlightenments. So, to commemorate this event, let us take a virtual picture together. So, we will kindly ask the Creative Division to lead the documentation session. Thank you, Creative Division.
Dia bergantung kepada
Oh,
orang
ya,
yang
ya.
yang pemimpinnya. Dia tanya.
Ladies and gentlemen, distinguished guests, with the photo session, we have finally reached the end of this event. But before that, we would like to announce our best questions winner. Congratulations to Veriona and Carol. Please drop your full name and phone numbers. The committee will contact you shortly regarding the prize.
Once again, congratulations to the two winners with two best questions. On behalf of the committee, we would like to once again thank Dr. Teknomo and Ms. Nova for joining us and giving us the knowledge about the role of ideal flow network in current society's issues, and to thank all parties that have been involved in the success of
Please
this
allow
event.
us to close this event in a prayer as well. And I will lead the prayer in a Christian way. Heavenly Father, thank you for your guidance and blessings throughout this colloquium so that this event can work well. We hope that through this colloquium, we can learn new things, get knowledge, and also get a deeper understanding about IFN Transport. Thank you, Lord. In your name we pray. Amen.
Before we close our event, we would like to remind all participants to please fill in the Regis Out form that has been sent through the chat section before leaving the Zoom meeting. Once again, I am Tamara Regina from International Business Engineering Class of 2021.
And I'm Jesslyn Maria from International Business Engineering Class of 21. We'll see you all in the next event. Bye-bye.
Bye.